Quantum entanglement. From Einstein's skepticism to technological breakthrough quantum entanglement, a phenomenon once dismissed as spooky action at a distance by Albert Einstein has evolved from a theoretical paradox into a cornerstone of modern quantum technology. The debate surrounding this bizarre property of quantum mechanics, which allows particles to remain correlated regardless of distance, has spurred decades of research culminating in practical applications like ultra-secure communication and advanced computing. The origin of the spookiness in the 1920s, Einstein, along with Boris Podolsky and Nathan Rosen, questioned the completeness of quantum theory. They argued that if quantum mechanics were correct, it implied an instantaneous connection between entangled particles, violating the principle of locality. The idea that an object is only directly influenced by its immediate surroundings. This led them to propose the existence of hidden variables that would predetermine particle behavior, eliminating the need for instantaneous influence. However, physicist John Stuart Bell developed a test in the 1960s to determine whether these hidden variables truly existed. Bell's theorem predicted that if local realism, the combination of locality and hidden variables, were true, certain statistical correlations between entangled particles would be limited. The experimental verdict decades of experiments, notably those conducted by Ronald Hansen at Delft University of Technology and others, have decisively confirmed that Bell's inequalities are violated. The 2015 experiments, earning 3 physicists the 2022 Nobel Prize, proved that quantum correlations are stronger than any local realistic theory could allow. As Marek Zukowski of the University of Gdansk put it, that was the final nail to the coffin of all those ideas. This means that entangled particles exhibit a connection that transcends distance and classical physics. They aren't merely correlated by shared past information. Their fates are intertwined in a way that defies conventional understanding. From paradox to practicality, the acceptance of non-locality has unlocked real-world applications. Hansen's work, initially conceived as a test of quantum advantage, paved the way for quantum cryptography. By leveraging entangled particles, it is possible to create communication networks that are theoretically unhackable, because any attempt to intercept the transmission would disrupt the entanglement, immediately alerting the users. Quantum computing also relies heavily on entanglement. Entangled qubits, the quantum equivalent of bits, allow for computations that are impossible for classical computers. Researchers are actively exploring how to harness entanglement to create more powerful and efficient algorithms. You can't escape non-locality, says Jacob Behrens at Harvard University, underscoring that this fundamental aspect of quantum mechanics is not just a theoretical curiosity, but a foundational principle for future technologies. Entanglement remains a subject of ongoing research, with physicists continuing to probe the underlying assumptions of Bell's work. However, it has already transitioned from a philosophical debate to a powerful tool for innovation. The initial resistance to quantum non-locality has given way to a new era where embracing this spookiness drives progress in secure communication, advanced computing, and a deeper understanding of the universe itself.